Good morning, everyone. Let's continue where we left off. Yesterday, we were looking at how does a HSQC pulse program, pulse sequence look. We did draw where we had the first inept, which transfers the polarization from proton to carbon. Of course, the third pulse or the second 90 pulse in the proton should be orthogonal to the first one. So I'm putting it as Y. Then after that, you have the T1 evolution on carbon dimension, where the 180 pulse is applied right in the middle of the T1 evolution. Then you have the reverse inept, which takes the coherence back or the polarization back to proton, where the tau delays are carefully set to 1/4J. And then you end up acquiring in the proton channel with decoupling in the carbon. This was a pulse program that we looked at. And we were trying to understand how does the density matrix formalism work out. The initial part, we started with HZ, and due to this, it will end up going to something like 2HZ-CY. And since this term will only evolve with the carbon chemical shift. Carbon chemical shift gets encoded in the T1 period, and the tau 180 tau, when the 180 only being on the proton, takes care of decoupling, and then you transfer it back where you will have the cosine modulated signal in T1 times a certain operator for proton, the first single quantum operator, which can be therefore observed. And you have the acquisition time T2 in the direct dimension with decoupling done, just so that only proton chemical shift evolves and there is no evolution of the scalar coupling between carbon and proton. This is what we had done. I had also asked for a question here where I say, remove the 180-degree pulse in the middle of T1.
Sir, I based that 90-degree Y to 90-degree X. The 90-degree X we took after tau 180 tau in the first phase.
So what you did was you changed the phase of this pulse. Okay, in the class, I think we kept it as X, is that right?
Yes.
And the second cycle, you said you changed it to Y. What was the receiver phase that you had kept yesterday?
At -X.
-X, right? So you tried that, and were you able to get the sine component of it? So now you are convinced that if you change the phase of the first pulse before T1 evolution, whatever creates the coherence just before the T1 evolution, if you change the phase of the pulse by 90 degrees, keeping the receiver phase constant, you agree that you get the quadrature, meaning that if you use X, you get the cos omega C T1 modulation. If you end up using the Y, you get the sine omega C T1 modulation.
Yes.
You're convinced about it now? Good. There's another problem that I had given, which talks about carrier frequency and spectral width. Yeah, so we were talking about what will be the carrier frequency for a spectral width that spans 20 ppm from 80 to 100 ppm in carbon. Where would you keep your carrier?
Sir, proton 5 ppm.
Very good. Proton should be 5 ppm. They should be carrier. And then how about, so 90 ppm for carbon and 5 ppm for proton. That is correct. And how about question B? What is the spectral width in ppm for carbon? What is the spectral width for carbon?
20.
Very good. Spectral width of carbon in ppm is 20, and spectral width of proton?
Yeah.
Very good. Excellent. What is it in hertz for 400 megahertz?
4 kilohertz.
4 kilohertz. Excellent. And how about carbon? 2 kilohertz. Yeah, that's correct. 2 kilohertz. So what is the dwell time for carbon?
500 microseconds.
500 microseconds. And what is the proton dwell time?
250.
Yeah. Slowly, you guys are able to observe that the dwell time is just dependent upon the frequency in hertz. If you increase the spectral width by half, going from carbon to proton, you see that the dwell time just gets halved. 2 kilohertz, you are 500 microseconds. Doubling the spectral width only reduces the dwell time. It doesn't depend on the gamma. Do you see that? If you increase the spectral width by 2 times, the dwell time reduces by 2 times. because it's a 1-over relationship. Okay, slowly this should start coming in your head as you change the spectral width. How does the dwell time change? If acquisition time for proton is set at 100 milliseconds, what is the number of points in proton, real points? 0.4 points. Careful. So you have 100 milliseconds and the dwell time is 250 microseconds. So how many is the total number of real points? Did you make a mistake there by chance? That's okay.
The acquisition time is 3 times T2.
But I didn't tell you what is T2. I gave you what is the acquisition time. No, this is small t2, my dear friend. I would have written capital T2 and capital T1, right? No, this is small t2. Okay, good that we had this confusion. So be a little careful about it. If this is the case, you guys might have set the acquisition time to 300 milliseconds. Is that right? Is that right, Gaurav? Okay, let's take that as the example. If you had it as 300 milliseconds, what is the total number of real points, Gaurav?
I got the 1H of 1H, I got 400.
What's that?
2.4K points.
2,400. You see, number of points you should be careful about. You can't say 2.4 thousand. Sorry?
It should be divided by 10.
No, not, you don't have to divide it. Okay, so, okay, what is the K then? Go ahead.
If I have
You don't have to convert to K. You tell me the number. That's fine with me.
2 zeros.
Literally 2,400,
Yes.
right? Okay, good. 350 by 300 by 250 cannot be that. What's that?
100 by 250.
Okay, wait a minute. Let me just go back to what I gave you. Okay, let's go to, this is what you guys want to do now? Okay, so let's say that is what you have. Let me give you the answer because we are taking a little too long for this. Please go and practice 2 by 5, 10 power 3, which is 2000 by 5, which is 400 real points. So the total number of points should be 800, where 400 is imaginary, 400 is real. Okay, so similarly, the TD by 2 for carbon will be 32 milliseconds divided by 500 microseconds. Right? So what is that going to be? 1200 points. Is that right? Seems a little high to me. So let's see again. Maybe you're right. I just want to make sure. 32 times 1000 divided by 500, 64 points. See, 32 milliseconds, 500 microseconds. 10 power minus 3, 10 power minus 6 gets cancelled and you get a 10 power 3 on the numerator. 1000 by 500 is 2, so 2 times 32 is 64. Okay, so kindly, I guess people are making some small errors here and there. Please be careful about calculating the number of points.
Sir, I have made mistake while writing the question.
That's okay. That's the purpose that these questions were given. This is how your quiz 2 will be, which is going to happen in about 2 weeks. So start working out on how these numbers work out. I'm going to show you some examples in the spectrum today. Okay. All right. So those 2 homework, I think I gave one more. I forget what it is, but we can leave that. I gave a passive coupling. How many of you tried evolving the multiple quantum term with the passive coupling? Okay. So were you able to find the coupling come up in the indirect dimension? That's right. The 2 factor will just reduce the intensity by 2, isn't it? That's correct. Right. So what will happen is that the 2HXCX, once you evolve, let's say with the kth coupling, let's say the next proton is called K for sake of simplicity, you're going to get 4HXCXKZ. Of course. So the factor 2 will have to come in order to keep the operators normalized. Okay. So yeah, you're right. Of course, the intensity is going to half. We agreed on it, right? When coupling happens, it's going to reduce the intensity. So please work this out. This is a very important problem to understand how HMQC gives passive couplings. Could be an advantage or a disadvantage. Okay. All right. Yes.
Passive coupling is an example of IS2 system.
IS2. Actually, it's not IS2. It's more of AMX type system. Okay.
We have to consider three.
So the passive coupling, I thought I gave an example. Let me see. Yeah, for instance, you take this system. You're looking at this proton and the HMQC with respect to the nitrogen, let's say. Yeah. But now this proton couples with the H alpha proton, right? So this is like an, this can be thought about as M, this can be thought about as A, this can be X. So you're talking about AM and MX coupling with each other and AX coupling being rather weak. Okay. And therefore, you're trying to see how when nitrogen chemical shift evolution happens, the scalar coupling between HN and H alpha turns up coming in the spectrum. Make sense? Good. I'm happy that you tried.
Sir, I have a question. Sir, in this part in HSQC, we got two terms. One was of the cos component and one was having sine. But we evolved only cross component. That both of them were single quantum terms.
Excellent. Excellent question. Can we solve it right now? The question is, during T1 evolution, Gaurav, when he solved it back after he goes, he said that, okay, you just started with 2HZCY and you evolved it. But remember, there is going to be another component that will also evolve out of it. Why is that you are not bothering? So why don't we go back stepwise and get this done? You start with IZ. You apply a 90-degree pulse along X for I. You make it minus IY. The tau 180 tau period will only evolve scalar coupling, which will be minus IY since there is a 180. I think this will end up being plus IY cos 2 pi j tau. Then plus 180 on both. So this will still flip. And then you have 2IX SZ sine pi j tau. This is what you have. So when you set tau to 1 over 4j, what you end up getting is 2IX SZ at the end of this point. When you apply the 90-degree pulse along Y for I spin, 90-degree pulse along X for S spin, what you end up getting is that minus 2IZ will come up, IX will become minus IZ, and SZ, which will become minus SY, so minus of minus becomes plus. So at this point of time, you have 2IZ SY as your operator. So now the question is, when I have 2IZ SY, the tau 180 tau period, what happens? Or rather, the T1 by 2, 180 T1 by 2 period, what happens? Correct? We were able to see that the proton chemical shift will not evolve because IZ will commute with IZ. And we know for a fact that if you apply 180 only on the proton channel and not on the carbon channel, even the pi j HC IZSZ will also not evolve. So only term that's going to evolve is carbon chemical shift. So what are we going to end up getting? 2IZSY cos omega C omega S, because I wrote S here, omega S T1 minus 2IZSX sine omega S T1. The question that is being raised right now, we would have probably only gone ahead with this. Why are we ignoring this term? That's a very good question. We'll first see, will we follow through what happens? Shall we follow through the entire pulse program? The next pulse is a 90x on both channels. So what are you going to get? The Z will become minus IY. And the 90x on SY will take it to SZ with a plus cos omega S T1. Similarly, the 90x on Z minus Z is going to take it to plus Y plus 2IY with a SX sine omega S T1. Is that correct? Right? Now, what is left here is that this is still a single quantum term, but if you see, this has become a multiple quantum term. Okay. then you might always argue that there is a tau 180 tau that is still left and there is still a pulse being applied. Maybe it'll change the order of coherence. But we know for a fact that the 180-degree pulse will just flip the order of coherence. +1 will become -1, -1 will become +1, +2 will become -2, -2 will become +2. And 0 will remain 0. It's not going to do anything to it. So you are able to realize that during this period, this MQC term will remain MQC. Okay, and therefore will not evolve. So you can allow to evolve it and you just not observe it. And this helps you understand why is that we ignored it. There are other techniques, since you asked for it, there are other techniques called preservation of equivalent pathways, which I do not think I'll be able to get in this course. It's also called sensitivity enhancement in HSQC, where you'll use both these terms to get more, little more sensitivity. Okay, there we will end up exploiting. There'll be another 90 tau, 180 tau, 90 tau, 180 tau period that will come to enhance sensitivity. You don't have to worry about it. Okay, so your concern is correct. Why are we ignoring it? In this case, we'll ignore because we are doing a regular HSQC. We'll just take the single quantum term. In the tau 180 tau, scalar coupling will be active and this will end up becoming IX times cos modulation, minus IX or whatever. You keep the receiver accordingly. Make sense? So this is also important, but not for this experiment. You're not going to observe given this pulse program. You have to change it a little bit to recover something from this also. There are no questions. Let's continue ahead. What I would like to do right now is to give you a little bit of flavor from the experimental perspective on how a 2D spectrum looks. We have seen this quite a bit in the fact that we saw the one-dimensional spectrum of camphor. We also saw the help that it would do when it comes to DEPT experiments. So let's go back to the example of camphor. Count the number of carbons and protons. Look at the proton 1D, carbon 1D. Maybe start looking at the HSQC. And there are also other experiments that come handy, other 2D experiments. These are called proton-proton homonuclear experiments, which I have not discussed yet. Tomorrow's class will be only based on homonuclear experiments. The example that we have seen thus far in this course are heteronuclear experiments, meaning that you correlate a proton with carbon. You correlate a proton with nitrogen. You can always correlate a carbon with nitrogen also. Okay, these are called heteronuclear experiments because you're taking two different garomagnetically, you're taking two nuclei that have different garomagnetic ratios and you're correlating them with each other, right? On the other hand, you can always correlate proton to proton also. What benefit we get, we will see a little moment later tomorrow. Okay, those experiments are also important. But I just wanted to show you how does Fourier transform help. We have been talking about it so much. We'll take a look at the 1D experiment, do a Fourier transformation. Then look at how does the 2D help get frequency from the indirect dimension. I gave you an idea of what's an interferogram. Let's take a real example and see how does it actually come out. That will be the focus of today's class. Okay, so let's go one by one. Let me start with the proton NMR spectrum of camphor. So we also have to check what is the structure of camphor. So there are 10 carbons, 16 protons that are present in this chemical entity. And the structure of camphor could be viewed anyways. I actually like this one because it explicitly shows the methyl carbons. To make a note, there are 3 methyl carbons. And there are 2 quaternary protons, actually 3 quaternary protons. Do you guys agree on that? There's one on this bridge, and there's one, the tetrahedral carbon here, and there's also an sp2 carbon, which is a carbonyl. We have 1, 2, 3 methyl, we have 1, 2, 3 quaternary carbons. And then we have 1 CH2 here, 1 CH2 here, 1 CH2 here. There are 3 methylene groups. And there is 1 methine group, methine, methine, which is a CH group. This molecule was chosen so that you have all types of carbons. You have carbons with no protons, you have carbon with 1 proton, you have carbons with 2 protons, you have carbon with 3 protons. From the basic idea of chemistry, I'm sure you guys would understand the protons, the methylene protons, the CH2 that are being present here, unlike the case of ethanol where the methylene proton was chemically equivalent, in this case, they are not chemically equivalent because there are chiral centers that are being present. There's a chiral center right here. And also the entire molecule does not have any axis of symmetry, making the protons of the methylene groups unique. Why is this important? You will understand that therefore, although this is methylene proton, each of the proton will behave differently. It will couple with itself. These are geminal couplings, meaning that these are 2-bond proton-proton couplings. We are comfortable talking about 3-bond proton-proton couplings, but this also has 2-bond proton-proton couplings. So here life starts to get a little complicated because the chemical shift of the 2 protons will be close, where the scalar couplings will start to play an effect to give strong coupling effects. We will see some examples of this. I'm not going to end up solving the entire spectrum, but I'll just give you an idea to see how quickly NMR can help us understand. So let's start with the proton. How many protons did we say it has? It has 3 methyl protons. So let's zoom into the most upfield region. So we have 3 methyl protons, and I'm sure all of you guys accept these are all singlets, correct? Let's actually see the solvent. This is the DMS or D6 solvent that generally comes around 2.51 ppm. It's a quintet, which we have discussed before. Why is it a quintet? You guys know very well. The moment you go here, you are nicely able to see many protons. There is a nice doublet that's being present. You are able to see nice patterns of a doublet splitting further, isn't it? So this is a classic example where the methylene protons are identical. There are also some impurities, and then they further get split. This is a very complicated multiplicity to interpret by sitting just here. Able to realize that the spectrum is not very easy to pick up, especially for the methane and the methyl groups, given the fact that they have larger fine structure splitting. And I hope this also emphasizes the fact, you see the intensity of singlets versus intensity of the multiplets that are there. You start to see that as you have more and more coupling, well, it gives you good information. It also reduces sensitivity, and more importantly, it loses resolution. For instance, let's assume this is 1 proton. Are you guys able to see how much space it occupies? And it has too much information hidden inside it, right? Same example here as well. If you slowly pay attention, do you see mirror images of each other? There is one here, there is one here. So basically, it's a doublet that got split into further fine structure splitting. Okay, so that's what is happening here. Okay, with that being said, now let's go take a look at the carbon 1D NMR spectrum. How many carbons did we say exist? Let's count here. 1, 2, 3, 4, 5, 6, 7, 8, 9. We are able to count 9. The 10th carbon is actually a carbonyl carbon. It should come somewhere around 200 ppm. It has characteristics that are not easy to allow it for detection, meaning that it has a very long T1, it has a very short T2. The carbonyl carbon, the oxygen ends up taking the electron more towards itself. So the chemical shift anisotropy of the carbonyl carbon is high in general, due to which relaxation happens faster. Therefore, its T2s are shorter and its T1s are longer. Therefore, getting them in a 1D carbon NMR spectrum is not very easy. Okay, so unfortunately, you have to believe me when I say it would exist somewhere here. But otherwise, you're able to pick up every carbon. And of course, I don't have to say what this peak corresponds to. Can somebody tell me what this peak corresponds to? The solvent DMSO. That's correct. Okay, so there you go. And solvent has the most concentration. Therefore, it is the most intense peak. Therefore, we don't end up integrating and so on. We have already discussed all that, right? So now across the spectra, although you might be able to guess these 3 would be the methyl group, you're not able to see what is the CH2 or a CH group being present, or which is the quaternary carbon. And what should we do in order to understand that? We can do a DEPT experiment. So that's what I'm going to show you right now. I'm going to overlay. Let's do the DEPT 90 first. Why would we want to do DEPT 90? Only what signals will come if you do DEPT 90? Only the CH will come. CH2 and CH3 will go to 0 because you have a cos alpha component. If you set alpha to 90, cos alpha goes to 0. So you will only end up seeing the CH that's being present. There are also tiny signals that are coming up here. That's more of a leakage than anything. So one of the best things to look at would be the DEPT 135, which will give everything except for the quaternary. So let's see that right now. So you see that the blue does not show red or green. The red or green are the DEPT experiments. So therefore, these 2 carbons should be quaternary carbons, right? On the other hand, there are 2 closely resolved protons where the red one came up here, which we did say is the CH. So if you run the DEPT 135, it will come positive. you can phase it to positive. And you see the peak right next to is negative. So that indicates this is a, very good, that's a CH2, right? So now what you're also able to see here is that these two are also coming negative. These are also CH2s. And these three are coming positive, and that's not a surprise. It's a CH3, which we already know methyls are going to come upfield, and CH and CH3 will come positive. So this way, what you have done is that you can annotate your carbon one-dimensional NMR spectrum with which is a CH, which is a CH2, which is a CH3, and which is a quaternary carbon. If you're able to measure the carbonyl carbon, it'll come around 170 ppm, 170 to 200 ppm. So you should also be able to pick it very easily without doing anything in the carbon 1D. Make sense? Okay, now we have still done this. What we do not know, let's take the methyl group, for instance. You have 3 methyl groups, and therefore you have 3 assignments, potential assignments that are feasible. Correct? Which carbon goes with which proton? How would we get this?
2D NMR.
That's correct. Thank you very much. So we are better off doing 2D NMR. Let's take an example of a HSQC of the camphor molecule. Okay. We will look into smaller details as we go. What I'll first do is to overlay the proton. Let me remove the carbon 1D. I'll just show you the proton. So let's zoom in. You would see here that for every carbon, there's a slight mismatch in frequencies. This can be corrected with referencing. Okay, so now if you're able to see for every proton, you're able to get a methyl proton, you're able to get a correlation. Correct? Let's throw the carbon 1D spectrum also on top of this, and you will realize that for every carbon also you get a single correlation. And therefore, wherever the carbon and proton meet based on the experiment that you set up by setting carefully the 1/4J delay, are you able to see that this proton and this carbon are related to each other? Therefore, you get a 2D cross peak. For the methyl group, yes, you did know which are the 3 methyl protons. You did know which are the methyl carbons from the 1D experiments. But the 2D experiments help you correlate the carbon with the proton. Right? We still do not know. Now we know out of the 3 methyl groups, which carbon and proton go with each other. Okay, we'll come to asking now which methyl group is which one within the chemical structure a moment later. This course is not working towards that. This course is trying to say how does a spectrum come. But anyway, if I give you an example, it'll help you understand why such spectra are useful. Now that we have seen these ones, let's also throw the DEPT 135 so that you guys appreciate what we end up getting. These were the 2 carbons which we said are CH2s. Now, if you once again take a look at the proton NMR spectrum, there is something very important that you are able to understand and appreciate. The 2 protons that are coming here, you see how far they are split? They have the same carbon, but the proton chemical shifts are vastly different. That's because the 2 protons are diastereotopic and they talk to the same carbon. Now, slowly what you are able to see, oh, nicely I can patch up which 2 protons are from the methylene group, similar to what we did for the methyl group. Okay, let me repeat again. Would you agree that these carbons are methylene? How did we say that? DEPT is negative. Well, you are able to see this nicely. And if you go from this carbon, you see 2 proton peaks. Yeah, so therefore it is a methylene group. And why do you see 2 protons being distinct here? Because these are diastereotopic protons. And therefore, they share the same carbon because both protons correlate to the same carbon. So the carbon chemical shift is same, but the proton is different. And slowly what you're able to appreciate how far these 2 protons come up. These 2 are exactly, for instance, you can imagine this to be this proton that we are trying to look at. They're bonded to the same ones, very close in space, but you see how sensitive chemical shifts are. Maybe one is facing the methyl groups, the other is facing away from the methyl groups. That causes so much difference in the chemical shifts. And that's not the only case where you're able to see. The other case that you're able to see is also very similar. They're split quite significantly, isn't it? So it's one of the important take-home messages that you get. Okay, so those 2 are the methylene protons. And remember, we saw one more methylene proton farther away in carbon, which is close to the CH, right? This was a CH, which is only giving 1 proton again. This is a CH2. So you're confirming that the carbon still has 2 protons by also this experiment. So this way, what you have done, yes, you have carefully mapped which carbon has which protons. We still do not know within the chemical structure, where do these methyl groups come up? Right? But you have identified which is methyl, which is methylene, which is methine, and which is quaternary carbon. Agree? So slowly what we are able to understand and appreciate here is that as you keep adding more and more NMR experiments, you can get atomistic resolution of what you want to study. What do we mean by this? Let's say you take camphor. Let's assume that we have the ability to convert this proton to something like else. Let's say a chlorine. If you end up substituting it to a chlorine, would you agree that the chemical shifts will change because a chlorine would have different electronic effects than a proton? And in addition, you are reducing the hyperfine coupling splitting between protons and scalarly coupled protons. And therefore, the NMR spectrum would change. Is that right? So it's a very important marker to understand what changes have happened and whether you synthesize the right molecule. This is predominantly the way chemists end up using it. On the other hand, how would we end up using this is that, just for an example I'm giving, let's say there is a host-guest relationship of camphor with something else. There's an interaction of camphor with some other molecule. Let's say I add that molecule to camphor, the chemical shifts will change upon interaction. Therefore, I can study how the chemical shifts are changing to talk about, okay, whether an interaction is happening, what is the binding constant, and other necessary thermodynamic and kinetic parameters can be quantified with other NMR experiments. So I hope I'm able to push the point that the chemical shift are very important parameters. You can do a simple 1D, like the 1D proton, 1D carbon. But if you start to do multiplicity editing with the DEPT, you can add additional attributes to the carbon NMR spectrum. The moment you do a carbon-proton correlation to get the single bond experiments, you will also be able to get, which is a CH2, CH3 carbon-proton chemical shifts correlated. Right? So far, so good. So I'm now going to remove the 1D NMR spectra from this. Let's take a look at the 2D and look at its beautiful glory here, where we are able to get so much information from it, right? I'm going to add one more experiment, which we have not discussed in the class yet. This is called the HMBC. Heteronuclear multiple bond correlation spectroscopy. The reason why this is important is that the HSQC gives you the single bonded CH protons, while the HMBC can give you HC couplings that are more than one bond away. I'll show you to make you understand what it means. So what you're able to see here, let's just take the methyl group. Are you guys able to see extra resonances from carbon going to a different proton? This indicates that the protons that you're trying to look at here are also close to these carbons in chemical space. So instead of jumping just one bond, this jumps more than one bond. So this way, what you have done, you know what's a CH, you know what's a CH2, you know what's a CH3. Now using this experiment, okay, I know this CH2 is talking to one CH and one other CH2. So slowly you will be able to stitch it across and say which carbon and which proton belongs to which entity in camphor. Go back and think about this. It'll make a little more sense. Look at how does an HMBC experiment work. So for instance, I'll take one example of this. Take this methyl group. You do not know where it falls, but now you're able to see that that methyl group talks to only one CH2 group. Why? Because this is a CH2 carbon. This is a methyl group, isn't it? And you're able to see that one ends up discussing with this one. So let's go take a look at chemical structure. And why am I not taking these? Because you are also able to appreciate the fact these two methyl groups have something that comes up that's not present in a HSQC. What will not be present in a HSQC? You will not see quaternary carbons. Okay? You did not see quaternary carbon. And now what you're able to see in the HMBC, one of the quaternary carbon does come up. You see that's in the red. So what does this indicate? Let me zoom in to show you. This indicates that this methyl talks to only one quaternary carbon, while this methyl and this methyl each of them talk to the same quaternary entities. Right? Does that make sense? Right. So go back to the structure. what you're able to see, there is one methyl group that talks to one quaternary carbon. There are two methyl groups talk to the same. So therefore, you can use all this information together to get atom-specific assignment across carbon and proton within camphor. Of course, you can only not get the assignment for oxygen because it's NMR inactive. Okay, so this is the way NMR helps. So there are other experiments which are proton-proton correlation experiments that help you get more information. But the main thing that I promised you guys is to show you how does the interferogram work? How do you get the indirect dimension frequency? So let's go back to the HSQC spectrum. So everybody accepts how the spectrum looks. Everybody is able to connect how the 2D goes to the 1D. Sorry. Everybody accepts how the 1D goes to the 2D and how we can make correlations, right? Now, let's actually look at the FID. These are the FIDs that are present. So let me zoom in. So there are many scans that are acquired, okay? Let's ask some of the crucial parameters. So you can ask spectral widths. The spectral width for proton is set to 5 ppm. The spectral width of carbon is set to 60 ppm. Okay? And the carrier positions are called with O1p. The carrier for proton is kept at 2 ppm. The carrier for carbon is kept at 35 ppm. So the carbon goes 35 plus minus 30, which means it goes from 5 ppm to 65 ppm. While the proton goes from 2 plus minus 2.5, which is minus 0.5 to 4.5. This is chosen in a way where you only want to pick up what you want to see. You don't want to see, although we keep saying 0 to 10 ppm, camphor does not have until 10 ppm. So you can cut it short and just see where you want to see. So this is the, let me see, SWH is a spectral width. And if you're able to see, this is a spectral width for proton. Let's try to calculate what is 1 over this value times 10 power 6. So you guys get something like 94.67 microseconds. I multiplied by 10 power 6 that you can see in microseconds. Do you see that value exactly come up here? 94.6625, 94.6679. Until the nanoseconds, it's correct. Right? So that's how dwell time gets determined. Okay? And the number of points that are, total number of points that are present, the proton dimension is 512 points. In the carbon dimension, we have acquired 256 total points, complex and real. Meaning that it's 128 real, 128 imaginary. Meaning 128 has, let's say, X phase, 128 has the orthogonal Y phase to get the cos and sine part. Makes sense? This is called quadrature detection. Okay. So with all this out, we said that the first thing that we get is cos modulation of exp I omega h t2. Therefore, we can do Fourier transform of the proton dimension to get the spectrum. Let's actually do that. Let's do process spectrum. Let me say process only F2 axis, meaning that Fourier transform only the proton dimension. The moment I do that, what you'll be able to see here, let me overlay the proton 1D here. You'd see that for every proton signal, you have something else going on in the indirect dimension. Remember, I'm not Fourier transform the indirect dimension yet. I only Fourier transform the proton. So therefore, the proton chemical shift gets properly picked. True? Now let's ask, what is this interferogram? Let me do this for you guys now. Just one moment. Okay. Let me pick this one to show you the interferogram. Right. I'm just picking one example. Index 817. I'm picking the column now. I'm just going to that chemical shift. If I keep my mouse here, on the top, you see there is an index 818. You see one of the numbers, it says column 2.505 ppm, 1754.4906 hertz, index 818. I'm going to take this index, meaning that I go to this proton frequency and extract all the values from the column. Shall I do that? Let me do that. RSC, if you hit this, it's going to ask which column to take. I just picked up 818 because that's where I have my signal. And then I'm going to put it in one process part of the spectrum. Let me not show data points because it's a little confusing. I'll just show the oscillations. Okay. This is called the interferogram. I went to the proton frequency and I said that the proton frequency will get modulated based on the T1 time and the carbon chemical shift. Are you guys beautifully able to see a frequency that comes up? Right? If you slowly sit and now we can show the data points again, so that you guys understand one more important information. If you sit and count in this, you will be able to count 128 points. You might ask what's happening after those 128 points. We have done something called zero filling. All those are just zero. These are just padded. You just put those numbers yourself. Okay. Until this cursor point is where we have acquired some real data. Anything after that is called zero padding. It has its advantages, which I don't want to go right now. Are you guys able to pick up there's a frequency nicely that's coming up because that proton is associated with a single carbon frequency? Make sense? Excellent. So this is how 2D NMR works. This is why it's called indirect dimension. You don't get this frequency directly. You keep changing T1 one piece at a time. So the first experiment, would have been at 0 dwell time. There you go. The first point that's acquired was at 0 dwell time, which is at the edge of the cursor. The next point that is coming up is measured at the first dwell time. What is the first dwell time? It happens in such a way that it's 93.57. I mean, you just calculated it, 93.66 or whatever, 94.66 or whatever, right? The next point will also be carefully measured at the exact same interval. I'm not measuring it precisely, but if you sit and measure it, the timing will be perfectly matched. So what you have done, first point you acquired 0 dt1. Next point you did 1 dt1. Next point you did 2 dt1, and so on and so forth to collect a total number of points. Total number of 128 points. How did we get to this 128 points? You had a certain spectral width. You wanted a certain acquisition time to give you a certain resolution in the carbon dimension, and you decided all this. Now, would you agree that if I Fourier transform this dimension, I'll get a carbon chemical shift? That's essentially what is done when you say, when you go to the 2D spectrum, it's still an interferogram. Basically, you have only Fourier transformed the proton dimension, not the carbon dimension. The moment you go here, now you say process F2 and F1 axis together. Hit enter. If you end up hitting enter, you get the 2D spectrum. Makes sense? Okay, that's how a 2D comes out. In order to see how the pulse program looks, you can type this command called show pp. What you guys are able to see in this example, the camphor example, the pulse with 90 degrees at high power was applied at 7.8 microseconds, 7.75. It's written right here. The phase is set to 0. In this spectrometer, if you set phase to 0, it means it's X phase. You have a certain time delay. You have a simultaneous 180 that's applied. The top channel is the proton channel. The second row is the carbon channel. Do not worry about the last part. Forget it for the time being. Okay. But what you're able to see here is that proton 90, tau, simultaneous 180 on proton and carbon. There's exact same tau delay. There's no difference. And then the simultaneous 90 applied on both. This is basically the inept module. And what you're able to see, if the first pulse is set at pH1 of 0, which is the X phase, you see that the third pulse is set at pH2 of 1, which is Y phase. These are the theory that you learned where you end up keeping the phase orthogonal to one another, you generate the single quantum coherence term. Then in this part, you see D0, which is T1 by 2. You apply the 180 degree pulse right at the middle of T1 by 2, and then you have T1 by 2 again. I have not introduced water gradients to you guys, so you can practically ignore portions from here to here. Forget that this portion exists right now, okay? Because gradient has not been introduced to you yet. I don't know whether I'll have time to introduce it at all. But are you guys able to realize from here to here, it's the inept that we just drew in our this thing. You have the inept and you have the frequency labeling, the decoupling on the proton, right? And from here to here, once again, forget this thing, is the reverse inept. Simultaneous 90, you have the tau delay, exactly the same tau delay that was said, simultaneous 180, and then the tau delay does come up here. It's adjusted for this pulse, but don't worry about it. The total time from here to here will be properly matched to 1.72 milliseconds. 1.72 milliseconds, 1 millisecond plus 711 microseconds, so it will be 1.72 milliseconds. And then what you end up doing is to acquire the FID and you decouple the carbon. So this is what we learned. This is how the pulse program looks. And in reality, if you have to understand how this is all coded, you can open the Pulse program where it has a little bit of complicated commands that are given, but this is basically a program that is written to say, okay, apply a pulse on the proton channel. Simultaneously apply a pulse on the proton channel and the carbon channel. Okay, and in between them, allow a D4 delay. Okay, and the D4 delay will be set as 1/4J. So D4 delay is set as 1/4J, where constant 2 is the J coupling value. So we can ask what is the J coupling value we set this experiment to. We set the J coupling to 145 Hertz for the carbon proton. Compromise of 125 for methyl and maybe a little more for the CH, 170 or something like that. Make sense? So what we have done today, we have not done anything serious. All that we have done is to revise some of the concepts. Some of the things that I told will be modulated. I just showed you with a real data that's been acquired for camphor and how does a spectrum get acquired. So we can also see the FID. All these are series of FIDs. These are repetitions of 1D experiments. How many times is the 1D repeated? So we'll see 1TD, at least 256 times it's repeated. And what is the number of scans? Each experiment is repeated twice for doing something called phase cycling. What is the D1? What are the number of D1 is 1 second? What are the number of dummy scans? 32 dummy scans were applied. Total number of scans were 2. And then you can all put it together and also estimate what will be the total measurement time for something like this. Slowly, we have built up from understanding the theoretical concepts of what's an alpha spin, what's a beta spin, how does the magnetization come, how do you perturb it, to actually practically applying it in a real life scenario. If you guys are able to understand what's 1D NMR, what's 2D NMR, going to 3D NMR is obvious. You just add another dimension. Just add another T1, T2, T3 instead of just T1 and T2 in this. That's it. The question is, how do you end up transferring polarization to do, how many chemical shift labeling will you do? Maybe if you have an HCN, you will label the nitrogen, you label the carbon, and you'll come back to the proton and detect and actually correlate the HCN. Only when you have the HCN bond, you will get a peak. That's a 3D experiment. That's about it. Try to go revise, think about what was spoken, and then come back for tomorrow's class. Please solve without the 180-degree pulse. Since you guys, for the HSQC, in the middle of T1 delay. One more assignment would be, do not change the 90-degree pulse in proton to orthogonal. Keep X and X and see what you get. Okay? Thank you very much.